Okay, limits at infinity. So the premise here is we want to know what a function does as the x's go towards infinity or possibly negative infinity. So that just means as your x's get bigger and bigger and bigger, are your y values leveling off somewhere? So typically what we're going to be looking at here is we're going to be looking for horizontal asymptotes. Is our graph approaching something as our x's get bigger or smaller in terms of going toward infinity or negative infinity? So question here is, what is the limit as x approaches infinity of x squared minus 1 over x squared plus 1? And I have that thing graphed. So if I graphed x squared minus 1 over x squared plus 1, that is the red graph down here. And what I want you to see is as your x's go towards infinity, now we're only seeing from negative 6 to 6, but if I were to continue to make these x's go towards infinity, I want to know, are my y values leveling off somewhere? And you can see that because I already drew the horizontal asymptote there, but our y values for this function are leveling off at 1, and they will never cross or actually equal 1. It will just continue to approach 1 as we go towards infinity. So the answer to this is 1, because as my x's get closer and closer to infinity, I keep on going to the right, my y value would keep on approaching 1. So here are some definitions and what that's saying. Basically, we have a function f. The limit as x approaches positive infinity means that our y values get close to that L as long as our x's are getting sufficiently large, so getting bigger and bigger and bigger. Same thing on 2 here. If we approach negative infinity, that just means getting smaller as we go towards the left forever. And then it says the line y equals L is a horizontal asymptote if either the limit as x approaches infinity is L or the limit as x approaches negative infinity is L. So the only way that we have a limit as if x approaches infinity or negative infinity is if there is a horizontal asymptote in our graph. So in this function, we want to find the limit, the infinite limits, the limits at infinity, and asymptotes for the function. So I'm going to start with the limits at infinity. So I want to know, what is the limit as x approaches infinity of this function f of x, and what is the limit as x approaches negative infinity of f of x. So this means that our x's are going towards infinity. Where are our y values going? So if the first one, the limit as x approaches positive infinity, I want to look all the way to the right side of my graph and say, is this thing leveling off somewhere? And yes, it is. As we go to the right forever, our graph is leveling off at a y value of 4. And then the same thing, the limit as x approaches negative infinity would say go to the left forever, and are the y values leveling off somewhere? And again, they're leveling off at 2. Just from the top of 2, but that's still fine. They're still leveling off at 2. Okay, so that answers that part. The infinite limits would say at what x values do we have an answer of a limit that is infinity or negative infinity or whatever. So where does that happen? Well, as our x values approach negative 1 from both sides, right, we have a vertical asymptote there. So as the x values approach negative 1, the limit is a positive infinity. Also, if we approach 2 from the left, okay, so 2 from the left, so here's 2. As I approach 2 from the left, the y values are going towards negative infinity. And if we approach 2 from the right, then the y values are going towards positive infinity. So those are our infinite limits. So infinite limits mean that the answer is infinity. At what x values does that happen? The limits at infinity are saying as your x's go towards positive or negative infinity, where are your y values leveling off? And then what are the asymptotes? So I'm going to go through and list what the asymptotes then are. We have vertical asymptotes at x equals negative 1 and 2. Right? That means I have a vertical asymptote here and also at 2. Right, we've got vertical asymptotes at -1 and at 2. We have horizontal asymptotes at y equals those places where the graph leveled off, which was at 2 and at 4. We have horizontal asymptotes at 2 and at 4. Now, horizontal asymptotes act differently than vertical asymptotes. A vertical asymptote, the graph is never allowed to cross that. But a horizontal asymptote, your graph, and you can see this, our graph does cross those horizontal asymptotes, but the horizontal asymptotes only affect what's going on as the x's go to negative or positive infinity. Okay, so calculating limits at infinity. If we want to know what is the limit as x approaches infinity of some function, how do we do this? We can't technically plug in infinity. We can think about that, but that doesn't really help us here. And the reason it's not going to help us on this problem is because we're going to get, essentially, if I plug in infinity, I'm going to get infinity over infinity, which we need to know how to relate that. I can't say that that's 1 because those infinities could be different infinities. So here's how we're going to handle this. If your fraction, if you have a rational expression where you have a fraction of two polynomials, what we're going to do is we're going to look on the bottom, and we are going to take the highest exponent on the bottom, which is x squared, and we are essentially going to divide everything on top and on bottom by x squared. Okay, so if that highest exponent was 3, we would divide everything by x cubed. So we're gonna divide everything by x squared, or multiply by 1 over x squared. What that's going to give us is the limit as x approaches infinity, and I'm going to go through and say if we divide every single one of these terms by x squared, what do we get? Our leading term would just be 3. Then x divided by x squared, that would be 1 over x. And -2 divided by x squared would be -2 over x squared. On bottom, we would have 5 plus 4 over x plus 1 over x squared. Now that looks uglier than what we just dealt with, but it helps us to get to the answer, because now if we think about the x's going towards infinity, what that's saying is our x's are getting really, really, really big. All of these things that now have x's on the bottom, if the x gets really big, what happens to all those? All of those things go to 0, right? If we keep dividing by a larger number, all these go to 0. So this goes to 0, this goes to 0, this would go to 0, this would go to 0, and what do I end up with here? I then just have this ratio of those coefficients, which is 3 over 5. And that's our answer. Okay, if you graph this function, you would see that you have a horizontal asymptote at 3/5. Number 2, again, we can't just think about plugging in infinity, because we would have essentially infinity minus infinity, which again, we can't say that's 0 because infinities could be different. So anytime you have a square root, and then plus or minus something not inside of a square root, what we're going to do here is multiply by the conjugate on top and on bottom. So we're going to multiply by the square root of x plus 1 plus x. So that would give us the limit as x approaches infinity of, on top, the square root of x plus 1 times the square root of x plus 1, x squared plus 1 is going to give us x squared plus 1. Those square roots would cancel. The two middle terms would cancel, and we would just have minus x squared when we multiply the last two terms together. On bottom, I'm just going to have the square root of x squared plus 1 plus x. So on top, our x squareds will cancel each other out. So we just have 1 over the square root of x squared plus 1 plus x. Okay, well, I'm going to use the same strategy as before, but it's going to look a little bit different here. So I realize that the highest exponent on the bottom is x squared, but that's inside of a square root. So what I'm going to do is I'm going to think about dividing everything by x, because the highest exponent on the outside of my square root is 1. But also, if I do square root of x squared, that would also be an exponent of 1. So I'm going to divide everything by x to the first. So on top, I would just have 1 over x. If I take, because the only thing left I have up there is 1. So 1 divided by x would be 1 over x. On on the inside of my square root, I have to disguise this as 1 over the square root of x squared, but that is the same thing, right? So I'm going to, on the inside of my square root, I'm going to divide everything by x squared. So that's going to give me 1 plus 1 over x squared on the inside of the square root. But then on the outside of the square root, again, I'm just dividing by x, which means that turns into a 1. Okay, so now everything that has an x on the bottom is going to go to 0 as the x's go towards infinity. So that goes to 0 and that goes to 0. So now what do we have? We have 0 over 1 plus 1, which is 0 over 2, which is still 0. Okay, so those are the steps you need to show in order to evaluate that limit as x approaches infinity. The last one, we're just looking at the sine function and what happens as x goes to infinity here. I'm just going to draw a graph of what the sine function looks like, right? It does this, and it continues on doing that forever as I keep going. So the question is, as your x's go towards infinity, as we keep going to the right, are the y values leveling off somewhere? Do we have a horizontal asymptote? And the answer is no, because these would continue to fluctuate between y values of -1 and 1 forever as we go off to the right. So this limit does not exist. Okay, lastly, we could have infinite limits at infinity, which just means that as your x's go towards infinity, so do your y's, or maybe your y's go towards negative infinity as your x's go to infinity. So an example of that would be, here's the function x cubed. So the function x cubed, remember, looks something like this. And the question would be, as your x's go towards negative infinity, in this case, we're doing limit as x approaches negative infinity. So as our x's go to the left forever, where do the y values go? And the answer here, if you just think about that, if you do negative infinity cubed, we take a very large negative number and cube it, we're going to get an even larger negative number. And so the answer to this is negative infinity. As we go off to the left forever, our y's are also going down forever. Okay. X squared minus x, what happens as the x's approach infinity? I'm going to graph this one because, again, if we plugged in infinity, we would have infinity minus infinity, and we're looking at a difference of infinities that we don't necessarily know how to handle here. So if we just take a look at x squared minus x, if you think about that graph, it's just a parabola, right? That's all it is. So what happens as our x's go to the right forever? Looking at the graph, it's just a parabola. If our x's go to the right forever, so do the y values go to the positive infinity. They go up forever, right? So again, it doesn't necessarily make sense to plug that in, but thinking about the graph, that makes sense. And then number 3, because we have a rational expression, I'm actually going to handle this the same way as I handled number 1 up here. I'm going to look for the highest exponent on bottom, which is 1. I'm going to divide everything by that. So I'm going to divide everything by 1. I'm going to multiply everything by 1 over x, or divide everything by x. So I get the limit as x approaches infinity of x squared divided by x is x, and x divided by x is going to be 1. So my top becomes x plus 1, and the bottom we would have 3 over x minus 1. Again, the things with x's on the bottom are going to go to 0 now, so that will go to 0. But if I think about plugging in infinity to all the x's here, what I essentially have is infinity plus 1 divided by negative 1, because that first term goes to 0. I now just have negative 1 on the bottom. Well, infinity plus 1, that's still infinity, but then if I divide by negative 1, I'm going to get an answer of negative infinity. So you have to be careful what that sign is and how that can affect that. You might just think positive infinity because of the top there, but we're dividing by negative 1, which means that we're then going to go towards negative infinity.